Okay, Math8A ladies and Math8A gentlemen and everyone in between. Today, we're going to move on into section 2 of chapter 11, and we're going to talk about graphing rational functions. First, we're going to have to figure out what a rational function is. So, what's a rational function? Well, here's an example of a rational function. Hey, that looks like what we were talking about yesterday when we were talking about inverse variation. So here's something about rational functions. They look like inverse variation. Now, why is this called a rational function when in math usually rational means like something that's ratio-ish? I don't see any ratios here. Well, this is called a rational function because if you write it in terms of y, you would divide by x, and you would get 12 divided by x is y, or what we would say is that y is always a function of the ratio of some number. It could be 12, yesterday was 1,000, or negative 32, whatever that constant is. It's the ratio of that number divided by x. So this is called a rational function because if you get the y by itself, you have y equals some kind of a ratio with an x in the denominator. Okay, so this is a rational function, and what we're going to work on today is how you graph a rational function. So how would we graph this? Well, let's just think about some numbers that would work here. So let's say when x is 1, 1 times what makes 12? 12. So you'd have some point way up here. When x is 2, 2 times what makes 12? 2, 6, 3 times what makes 12? 3, 4, 4 times 3. Looks pretty linear, huh? Interesting. Oh no, not exactly linear. 5, let's skip that. 6, 2. But then it would be 12, there'd be another dot somewhere over here, right? So what happens is, there's that kind of a curve that we saw a little hint about yesterday when we were talking about inverse variation. But we didn't finish graphing this function yet. Why not? Because negative 2 times negative 6 also makes positive 12. And negative 3 times negative 4, and negative 4 times negative 3, and negative 6 times negative 2 also work. So we have another curve. Isn't that interesting? It's like two opposing curves, like symmetrical curves over here, but one is in the first quadrant and one is in the third quadrant, and there's nothing over here in the second and the fourth quadrants. When you graph a rational function, you're going to get a pair of curves. And there's also some other interesting things going on here. What if x was 0? What would y have to be? Hold on. X can't equal 0, can it? Because there's no number that you could multiply times 0 to get 12. Therefore, this function has no value anywhere here. This curve is never going to touch that invisible boundary line. And it works this way too, because y can't ever be 0. So these curves will never stretch into the second or fourth quadrants because of these invisible boundary lines. If you recall, these invisible boundary lines have a name. We've talked about them before. They're called asymptotes, and they're basically invisible boundary lines that your function can never cross or touch. All right, now that we've seen a bit of an idea of what a rational function is and what the graph might look like, let's take a look at some more examples. How do you find the asymptotes and where they are? Is it always going to just be the y-axis and the x-axis? Not always. So for any other function that is a rational function or an inverse variation function, how are we going to know where those asymptotes are? To answer that question, I want us to remember something called the zero product property. If you recall, the zero product property says that if something times something is 0, either the first something is 0 or the second something is 0. One of them has to be 0, or else the product ain't 0. Remember that? Okay, now for this, we can't apply the zero product property, but if something times something is 12, we can say it's not that x is 0 or y is 0, it's that x can't be 0. And y can't be 0 either. So this is kind of like the opposite of the zero product property. When you have an inverse variation situation or a rational function, there are numbers that x can't equal and y can't equal in order for it to come out to that product. And that's how you find the asymptotes, is you find what x can't equal and what y can't equal for that function. Okay? So that's how you find an asymptote for a rational function. The problem is it's not always x can't equal 0 and y can't equal 0. For instance, for this particular rational function, what would our asymptotes be? Well, if I did it the way that we looked at our last problem, and I rewrote it like an inverse variation where it's something times something equals something, I would take this and I would multiply it over here, and I would say x plus 2 times y equals -4. And we basically have that quasi-zero product property kind of thing happening here, where basically if something times something equals -4, then this something can't be 0, right? Because then you'd have 0 times something equals -4, and that's impossible, right? And y can't equal 0 either. So what are our asymptotes for this? Our asymptotes are going to be x can't equal -2, right? And y can't equal 0. So when you graph this, you're going to have an invisible dotted line at -2 and at y equals 0. And your curves are probably going to look something like that. And that's basically how we would go about knowing where the asymptotes are for any given rational function. Now, what would the actual curves look like? And you should probably do a little bit of this, start plugging some numbers in, getting some numbers out to find out where the actual dots are for that curve. Because actually, here's a little hint. The curves aren't always upper right and lower left. It's possible that a rational function might have curves here and here. So you do want to plug numbers in and get numbers out, and plug numbers in and get numbers out to see exactly where those curves are, but you also need to find the asymptotes first to know where those curves are going to have their boundary lines. Okay, we did that one. Let's try one more. Let's say you have y equals 2 over x plus 1 equals -5. Now this one is real interesting. In order to get this to be something times something equals something, we're first going to have to add 5 to both sides. So I'm going to add 5 to both sides. That's going to go away, and I'm going to have y plus 5, right, equals this. Then wouldn't I have to multiply both sides by this to get 2 by itself and x plus 1 over here? Now, this times this equals 2 means this can't be 0. And this, whoops, can't be 0. Right? Because if this was 0, then this wouldn't be 2. And if this was 0, then that couldn't be 2. It'd be 0. So where are my asymptotes? I would have an asymptote at x can't equal -1 and y can't equal -5. what would the graph look like? The graph would look something like this. You'd have your y-axis and your x-axis, and when I go to graph this function, I'm going to have an invisible boundary line, although we'll make a little dotted line right here. At x equals -1, I'm going to have another boundary line at y equals -5, so somewhere down here. And then to see where that curve goes, we're going to plug some numbers in, get some numbers out, and see, is it going to go here and here? Or is it going to go here and here? Or would it be maybe these two or these two? It can't be those two at the same time, right? Well, I don't know. You got to do some input-output testing to see what happens. All right. That is how you find asymptotes and graph a rational function. We also want to know how to find something called an excluded value. An excluded value for a function is basically like an asymptote. Can you look at this and know what x is not allowed to equal? I think you can see that x is not allowed to equal 0 because you can't do 5 divided by 0. It breaks the laws of math. And you could also use that product thing like we did last time, x times y equals 5. So x can't equal 0 if the product is 5. We also know that y can't equal 0 for this one either. For some reason though, when we think about excluded values, in math that phrase only means what can't x equal. I don't know why. I mean, y can't equal 0 either, so to me that's an excluded value as well. It's probably a good idea to write both, but your answer key will only have the excluded values for x, not the excluded values for y. Okay, for number 2, what can't x equal? Well, you cannot do 1 divided by 0, and what would make this a 0? X can't equal -3. Do you see why? Because if you put a -3 there, you'd have 1 divided by 0, and you can't have that. What can't y be? Well, on this one, y can't be 0. Why can't y be 0? Because 1 divided by something is never 0. Think about that. You take $1 and you divide it into 10 parts, 20 parts, 30 parts, 100 parts. How many times do you have to divide $1 before everybody gets 0? In theory, it'll never happen. Everybody always at least gets a fraction of a cent. So y in this situation will never be 0 because 1 divided by something is always something, not 0. That's another way to think about how to find excluded values or even asymptotes for these kind of rational functions. Finally, on this one, you get some weirdness here because there's an x plus 2 on the top and an x minus 1 on the bottom. So what can't x equal? Well, it's only really the bottom that matters. Can the top be 0? Yeah, you're allowed to have 0 on the top of a fraction. Numerators can be 0, but can denominators be 0? No. So x minus 1 can't be 0, therefore x cannot equal 1 because 1 minus 1 would be 0, and you can't have that, it's impossible. Okay, that's how we find excluded values for a function. What else are we going to be doing in section 11 too? We're going to be identifying asymptotes and then graphing a function. What fun! This is going to be great. So, where are my asymptotes? For this one, x can't equal 0, y can't equal 0. So to graph this, you're going to do a nice job with maybe some graph paper and graphing it accurately, but we know that our asymptotes are going to be right there and there on the x-axis and the y-axis. You can try plugging some numbers in. Basically, what you'll get is a graph that should look like this for this function. How far apart will it be from the x-axis and the y-axis and the origin and all that? That's where you have to plug some numbers in to try to kind of get an idea of what those curves look exactly like, but that's the general idea. For this, it might be very similar to that, except we know x can't equal 0 because you can't do 3 divided by 0, but what can't y be? You could add the 1 over here, right? And then multiply both sides by x and do what we did before. But I have another way for you to think about this. Okay, so this can't be 0. 3 divided by something can't be 0. So y cannot equal 0 minus 1. Because this can't be 0. Oh, so what can't y equal? Negative 1. And that's going to be your vertical asymptote. That's going to be your horizontal asymptote. And from there, you should be able to graph the function. For number 8 on this problem, what can't x equal? X can't equal 2, because 2 minus 2 is 0, can't have 0 in the denominator. What can't y equal? Well, 1 divided by something is always something, so y will never be 0. There's your asymptotes, and from there you should be able to draw a graph. All right, so rational functions, not too difficult. They have kind of an interesting look to them with a double curve. We haven't seen that before, but I think you'll be able to get the hang of this. And your homework today is you're going to do some practice problems on page 687, and I gave you 2 bonus problems to do so that you can get extra credit